Okay, can everybody see my slides now? Okay, so we're in the second half of our lecture this evening. And as I told you, there is a handout that I posted in the chat. I'll also post it to our class's D2L homepage. And it is the resource sheet or the handout that you're allowed to bring into the exam, which is monitored by Respondus for the, exam 5. And it has a molecular orbital diagram for dilithium to dinitrogen, or to nitrogen, sorry, and from oxygen to dineon. So it has both of these MO diagrams. Now, again, what I just told my students, and I didn't record it properly, but anyhow, in our book, the convention that Chang uses in our book is that the 2px orbitals are used to make sigma bonds, and the 2py and the 2pz are used to make pi bonds. So again, you can see here that if we take our 2p orbitals, which are shown here, right? There's 3 2p orbitals from one atom and 3 2p orbitals from another atom, that we form from a total of 6 atomic orbitals, we form 1, 2, 3, 4, 5, 6 molecular orbitals, and this is the order in which they come. We've got 2p, or sorry, pi 2py, pi 2pz, sigma 2px, then we have pi star 2py, pi star 2pz, and sigma star 2px. And so we'd have to tally up the number of electrons in our atomic orbitals, and we would place them in the molecular orbitals in order. Now notice that this page here just covers the 2p orbitals. If we look at the full orbital diagram for the second period, and notice that this is what I had on the last slide. Notice that there's 2 different sets, right? There's a set for lithium to nitrogen, and then from O2 to F2, and Ne2 isn't even on here. They didn't show it because it doesn't form. That there's 2 different sets, right? There's this one here, and there's this one here. There's different orders. I'm never going to ask you about why the molecular orbitals come in different orders, but anyhow, let's just look at a couple of the examples here in order for you to follow, what the heck is going on. So, say for example, dilithium. Can dilithium exist? Li2, right? Is there such thing as Li2? Is that a molecule that could exist? I don't know. Well, if you look at the electron configuration for just the valence electron, okay, there are core electrons. They're left out of this table, so we'll just concentrate on the valence electrons. We know the electron configuration of lithium is 1s2, 2s1. So we're only going to focus on the valence electrons. That means that lithium has just 1 valence electron, right? 1. Well, if I'm going to make dilithium, I've got 2 lithiums. They've each got an electron. So according to this diagram here, in Hund's rule and the Aufbau principle, both of those electrons are going to go into sigma 2s. Now, if I want to calculate the bond order, right, for dilithium, what's it going to be? My bond order is going to be 1/2 times the number of electrons in bonding orbitals, 2, minus the electrons in non-bonding orbitals. Well, you can see there's no other electrons. So there's no electrons in any of the anti-bonding orbitals. And so it's 2 minus 0, so that gives us a bond order of 1. That means this molecule could exist. Let's try another one. And I'll erase all this. Okay, let's try lithium. And while I'm erasing this, you can maybe think about it. Okay, so what about lithium? Does that exist? We've drawn the Lewis structure of lithium, and we showed that it had a triple bond. That would mean that it would have a bond order of 3, right? Okay. Does molecular orbital theory prove that? Well, nitrogen has 1s2, 2s2, 2p, 1, 2, 3. That means it's got 5 valence electrons. 5 valence electrons. Now, if I've got 2 nitrogens, that means I've got a total of 10. If I fill them up in here, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, if I calculate the bond order is going to be equal to 1/2. What's in a bonding orbital? These 2 are in a bonding orbital, and these 6 are in a bonding orbital. 2 plus 6 gives me 8. What's in antibonding orbitals? I've got 2 here in antibonding orbitals, and I've got 2 here. 8 minus 2 is 6 times a half is 3. My bond order is 3, and that explains the triple bond. Was I circling the oxygen when I was supposed to be circling the nitrogen? Anyhow, you still get the same answer. Yeah, I have, look, let's do the bonding again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's good. And then I have 1, 2 in antibonding. Okay, there's my mistake corrected. So here's where we're going with all this. Does molecular orbital theory explain oxygen? Oxygen, as we said, its Lewis structure shows that it's got a double bond. That implies it has a bond order of 2. But according to where we started, it's also paramagnetic, meaning that it's attracted to a magnet. Well, molecular orbital theory can explain that. Let me show you how. If I calculate the bond order, it's 1/2 times all the electrons that are in bonding orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Subtract all the electrons in antibonding orbitals. 1, 2, 3, 4. 8 minus 4 is 4 times a half is equal to 2. Therefore, it explains that the bond order is 2. It has a double bond, but look, we've got 2 unpaired electrons in the pi star 2py and the pi star 2pz orbital. These unpaired electrons, right, explain why it is paramagnetic. And that's one of the shows the prowess, I guess, of molecular orbital theory. Well, let's look at the kind of question that you might be asked on your next exam where you'd have to apply this. It says, what if you have the N2 plus ion? It can be prepared by bombarding nitrogen with fast moving electrons. We want to predict its electron configuration, its bond order, its magnetic properties, and the bond length relative to the bond length of N2. Is it shorter or is it longer? Well, in the interest of sending myself the molecular orbital diagram, I'm just going to draw it out, which might take a second. So I'm going to reproduce in my own handwriting the molecular orbital diagram for Li2 to N2. So just while I'm doing that, you can try and work on the problem. I'll start with Here we go. All right, and then I'm going to copy this. So copy, paste, put this down here, and then we'll change all these to 1s. There we go. Okay, so for our N2 plus, we've got N2 plus. Well, nitrogen has a total of 5 electrons times 2, which equals 10. If I've got a +1 charge, I'm going to subtract 1, that equals 9 electrons. Okay, so I've got a total of 9 electrons. The first thing I want to do is figure out the electron configuration. I'm going to use this MO diagram. Again, this is the one for Li2 to N2 because we're doing nitrogen. I've got 9 electrons. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Like that. Okay. Now we're going to write out the electron configuration, but we're going to write it for a molecule. I still haven't shown you how to do this, but I'm going to show you right now. So the way that you write out the electron configuration is like this. You follow the molecular orbitals, and you have to use parentheses. Let me show you. So you start with sigma 1s, and there's 2 electrons in the sigma 1s. So you write the sigma, so this is the electron configuration. So you write the sigma 1s in brackets like this, and then you put the 2 on the outside. The next one is a sigma star 1s. You write sigma star 1s, and you put the 2 electrons on the outside. Next, you've got a sigma 2s, and you put the 2 electrons out here. Next, you've got a sigma star 2s. You put those 2 electrons. Now we're up to here. Oh, sorry, I did the wrong number of electrons here. I forgot about the core electrons. So it's 9 valence electrons, right, for my nitrogen, but I left out the core electrons. And there are so nitrogen has a total of 7 electrons. Sorry, I left out the core electrons. And since I have, so basically, if you're wondering what mistake did Mr. Dion make, the mistake I made is this. What I was doing when I said 5 times 2, 10 minus 1, I was just dealing with this part of the diagram right here. I left out the 1s, right? Because if I include the 1s, okay, let me show you how it would work out. If I include the 1s for N2 plus, well, nitrogen has a total of 7 valence electrons. 7 times 2 gives me 14, and then I subtract 1 for the +1 charge. That would give me 13. So that's what I'm doing right now. So I mixed up. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 10, 11, 12, 13, 13 electrons, like that. So I should have a total of 13 total electrons. The same thing, we'd get the same answer if I had just done the top part here and hadn't done the bottom. I'll even prove it to you, okay? But I want to write the whole configuration. So after my sigma star 2s, we'll keep going. I've got pi 2py 2. I'm going to run out of space here. Then I have pi 2pd 2, and then I have sigma 2px, okay, 1, like that. That's my electron configuration. Okay, that's the whole thing. Now, the next thing is the bond order. It asks us for the bond order. Our bond order, whether we use this way or this way, you're going to end up with the exact same answer. I can prove it to you. If I solve it in blue, okay, if I was to only use the top part here, I get 1/2 times the number of electrons in bonding molecular orbitals. 1, 2, 3, 4, 5, 6. So that's 6 minus 1, 2. Am I doing this right? No, I'm not. 1, 2, 3, 4, 5, 6, 7. Okay, there we go. So I've got 7 electrons in bonding, and I've got 2 in anti-bonding. So that's 7 minus 2, which is 5. 5 over 2 gives me 2.5. Look, if I tried the same thing using the whole damn thing, watch. I'll prove to you. The bond order in this case would be, watch. All the electrons in bonding, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be 1/2 times 9 minus all the electrons in antibonding. 1, 2, 3, 4. 9 minus 4 is 5. 5 over 2 is 2.5. So you'd get the same answer no matter what. So the fact that I kind of mixed and matched there a little bit doesn't really matter. Okay. And the next thing it says magnetic properties. You know, is this molecule going to be paramagnetic or diamagnetic? Okay. Which one is it? And since it has an unpaired electron, it is going to be paramagnetic, right? That's the definition. When all the electrons are paired up, then it's diamagnetic. And the last question is the bond length relative to N2, is it shorter or longer? Well, remember that the more bonds that we have, the shorter the distance between the two atoms. So if the bond order is 2.5, we know that the bond order in N2, right? N2 has a bond order equal to 3. And so this has a lower bond order, and so it's not a triple bond, it's not a double bond. It's like more than a double and less than a triple, and therefore it's going to be longer because it has a lower bond order. So we'll put here lower bond order equals longer. Okay, longer bond. All right. All right, this brings us to this section of delocalized molecular orbitals. I'm not sure what I would really ask about delocalized molecular orbitals, but the whole point behind the word delocalized is that their electrons aren't going to be stuck in one place, right? They're going to be delocalized, right? They're not in one locale, they're in more than one locale. Delocalized molecular orbitals are not confined between two adjacent bonding atoms, but actually extend over 3 or more atoms. An example would be benzene. If you look at the hybridization of all the carbon atoms in benzene, and this is the structure of benzene here, every single one of these carbons, okay, they're all surrounded by 3 atoms. So each one of those carbons is sp2 hybridized, and if carbon is sp2 hybridized, that means it's got 1, 2, 3 sp2 hybrid orbitals, but it's also got an unhybridized 2p orbital. So in benzene, you have 6, right? Since you have 1, 2, 3, 4, 5, 6 carbons like that, you've got 6 p orbitals that all overlap. See how they all overlap like this on the top and then on the bottom like that? So if you were to look at it with your eyeball on the side, it looks like, you know, you've got a cloud of electrons on the top and on the bottom. And what that does is it forms a conduit, if you will, because all of these orbitals are overlapping. This is looking from the top, right? If you're just looking down like that, okay? This is the top view, and you see that all those p orbitals are overlapping. What does that mean? What's the consequence of all those orbitals overlapping? Well, electrons are high energy. If they can move, they will. And since all these orbitals are overlapping, it provides a space for the electrons to move around between all of those unhybridized p orbitals. So a delocalized molecular orbital is formed by the overlap of all those atomic orbitals, and it allows the electrons to be even more stable. And so benzene is a very stable molecule. If you draw the Lewis structure of benzene, it's got 6 carbons in a ring like this with double bonds that alternate, and then each carbon has 1 hydrogen attached like that. Another example would be, and yeah, let's just keep moving on. Another example would be the carbonate ion, right? We looked at the carbonate ion, which is this right here, and we talked about the resonance structures, okay, of the carbonate ion. But if you look at the unhybridized p orbitals on all of the atoms in here, it forms a system where the electrons can overlap, or sorry, where they can move around, where they can be delocalized. And so all it does is it serves to stabilize the ion.